Now I would like to invite Milan Clover. He is a NERC Independent Research Fellow at the University of Oxford. He did his postdoc at the Massachusetts Institute of Technology, working on climate model development in Julia. He started speedyweather.jl, a global atmospheric model designed as a research playground to develop prototype ideas on machine learned representations of climate processes and computationally efficient climate models. He also worked on low precision computing, data compression and information theory, predictability of weather and climate, and software engineering. So.
Yeah, hey, I think I'm now the last one before the coffee break, so apologies for that, but I'll try to keep it quick. I want to talk for the next minutes about interactive climate modeling. So Speedy Weather is, despite the name, actually almost like more a climate model than it's a weather model. And in terms of interactivity, I often look up to Windy because I just find it amazing that this like software that people just put up, you can do it in the browser. You can just it just loads in the it has the weather forecast data in it, and then you can basically just like zoom around, zoom in, roll. You can see you can select different fields and so. And I have a vision that I want that to be a climate model where I can just say like I run it. You can press play and it runs forward and so on and so forth. And this is kind of the interactivity that I'm currently missing in climate modeling. And so basically to start, I pulled up from, actually this is October's last year, so it's from GitHub, just the statistics showing that Python is basically on track to be most popular everything. And one of the most striking metrics I find on this is the rise in the use of Jupyter notebooks in GitHub repositories. So that absolutely goes through the roof. And so I sometimes find it, if we talk about Python, I sometimes find it really useful. If you talk about Julia, I sometimes find it really useful to think about why a language like Python is actually so successful, right? So, I mean, it has a couple of years head start. Okay, get that. But it actually means that Python itself was so successful despite it not being really fast. But now people got basically the speed back in by just basically making it a wrapper around some C code. But it is definitely easy, interactive, cross-platform extensions. And software stack are always the things that everyone quotes when they say, like, why do you use Python? It's like, well, I have everything there. And of course, it's used for open source. And so this is something, I mean, obviously, I'm preaching to the choir here, what we already do in Julia as well, but we don't necessarily do in the traditional climate modeling community. And this is definitely something that's lacking. Because climate models have absolutely exploded in terms of complexity over the last decades. So the first, let's say, climate model you may think of is something that was probably formulated some 130 years ago or so, where C is just the concentration of carbon dioxide, and then with some baseline concentration, there's a logarithm in there, there's a parameter in there that you can train, and then you basically get your radiative force and you know how much warmer the planet gets. Okay, cool. This is a very, very simple climate model. Since then, a lot of things have changed. So the first models were on like atmosphere and ocean. And this is what we usually consider to be the computational fluid dynamics part of it. And then people over time have added atmospheric chemistry, what we just heard about, aerosols in there, biogeochemical cycles, carbon cycles, marine ecosystem, ice sheets, sea ice, upper atmosphere. So that's really above the troposphere, stratosphere, and so on. But also things like dust sea spray, carbon aerosols, interactive vegetation, and so on and so forth. And now there's obviously also models that even like simulate kind of human behavior in them. And so there is a massive amount of complexity in there. And I really want to distinguish this from the typical weather forecasting problem, even though a lot of climate models have been growing out of weather forecast models. How we use them is very, very different, because in weather forecasting, you essentially have a very fixed problem. You get some initial condition data, and then you press play, and you have something operational that needs to run a couple of times a day, and you have to always provide this data so that everyone has that available, and like agriculture knows this, sailors knows this, and so on and so forth. Whereas in climate modeling, we have a bit more time, so to say, and that also means that in order to understand the climate system, we do a lot of like leave one out kind of experiments, simulating counterfactual worlds, and so on and so forth. And so our need for interactivity is a very different one than compared to weather forecast models. What we actually solve are complicated equations, differential equations like this one. I just pull this up to show it's complicated. No one really has to understand this. Well, if you code it up, you do. And obviously, there's things like advection we just heard about, effects like Coriolis gravity, pressure gradient, viscous forces, conservation of mass is in there. Things like ideal gas law. If you do it in the ocean, you have a different equation of state there. And you have also like an equation for temperature. And even though this is already complicated, once you actually solve the entire climate system, this is from these equations are already missing humidity, clouds, precipitation, snow, radiation, surface fluxes, ocean, land, and so on and so forth, right? So there's a lot we have to account for. Nevertheless, if you solve these equations, and I'm just taking this here from Simone's paper from a few years ago. This is an oceanographic simulation just showing what happens if you run this on nicely efficiently on a GPU, blast the resolution really high. You already get an enormous amount of complexity in this is just the ocean. But you can clearly also see that there's a lot of processes that we need to account for and that we need to simulate that are even like left out here, right? Like all the land is gray. Right? So there's a lot happening on land that really affects us. Of course, there's also a lot happening in the ocean that affects us. And the atmosphere you don't even see because that's kind of like on top of it. And so that really shows the dimensionality of this problem. And so because there's a lot of these processes that we can't solve explicitly, so we cannot really think about these processes that are falling like through the grid cell, because we have to discretize things in some way, whether you use nice little square boxes or you use something different. But there's a lot of processes in the atmosphere and the ocean. Actually also like even in more spheres, but just focusing on these. For example, in the atmosphere, we have radiation, clouds, precipitation, kind of like every little symbol that you can see in this little zoom in plot there on the right. Convection, surface fluxes, turbulence, gravity waves. In the ocean, we have a lot of vertical diffusion and mixing that can't be explicitly resolved. Eddies and turbulence, you've just seen a lot of eddies, but of course, there's always a whirl within a whirl. So that's the whole dilemma of turbulence, is that it's always more turbulent if you increase the resolution. And yeah, interaction with bathymetry, because it's really difficult to resolve the bathymetry as its full roughness as it is in the real ocean. And then again, the surface fluxes communicating to atmosphere and ice and so on and so forth. So that gets enormously complicated. And so because of this complication, at some point in the last few years or so, I've realized that maybe actually our major bottleneck to better climate simulations isn't necessarily speed, but is actually interactivity and usability. And so I basically started the question like, okay, high performance computing is cool, I get it. But maybe as trying to give a little different perspective on some of the talks that we've heard earlier, I'm not sure that it's actually always the bottleneck to faster climate research and faster climate like knowledge that we gain about the climate system. And so basically asking the question of like, how do we actually accelerate climate research? Do we just get a bigger computer? Is that really going to help us? Or do we build our software in a different way to make to basically come quicker to solutions where then computing is not necessarily the bottleneck? And so going back in time, 1984, I think one of the first ocean models uses a so-called, in Fortran always called the name list. So there's a bunch of parameters in there. It's a text file. And then if you want your simulation to run somehow differently, that you would basically just go in and just delete the text and write something else in there. And then you basically just like on your compiled model, you press play, and then it would read those parameters in and compute this stuff. And so while this is somehow an easy interface, and I guess it's a fairly maintainable, maybe even interface, it really creates a situation where you can only change what the developer wants you to change. And I think this is, in weather forecasting, might be fine, because you can simply say like, well, I want to run a simulation from today, or I want to run a simulation from tomorrow, but everything else is kind of static. However, in climate modeling, because we have to understand so many parts about the climate system, leaving things out, simulating counterfactual worlds, and so on and so forth, we do end up in the situation that we have to be able to do the things that the developers don't want us to do. And so the old school models, I would summarize them as like, cool, we have the speed, great, they've been developed for decades with like tons of people, so we have the physical accuracy. They are doing a great job, but often they're not cross-platform. It like requires many people to somehow make them run on different supercomputers. Simply using it and putting another extension in it, also very difficult. Many of them are not even like properly open source, and they're definitely not easy and interactive to use. And so this is, I think, where we definitely want to, with interactive climate modeling, we definitely want to tick all those boxes. And so with the monolithic interface, or sometimes like this, it's kind of like thinking about you as being a user. You have the name list, you can press play, and then you run your simulation. It's kind of like sitting in a plane. You're the pilot, but it basically required a whole horde of engineers that actually built you all these buttons, and then you can use the buttons, but you can't change the plane. And so sure, we're not on the side, like at least with climate modeling, we're not necessarily concerned about all the safety aspects. What would happen if you were like halfway through flying, you would like change out your engine and you want to do something else. But this is exactly what we want to do in climate modeling, right? We want to sit in the plane, and sure, we want to use our knobs, but we also basically halfway through the flight, we want to say like, cool, what happens if I now use, I don't know, winglets, or I don't use winglets or so, right? And this is exactly the things that with a monolithic interface you can't do. Monolithic doesn't necessarily mean that it's not interactive. One of my favorite simple climate models is the En-ROADS. It's also just a website, maybe you know this, where you have a bunch of buttons at the bottom. So you can say, for example, I want to have a lot of carbon dioxide removal, like nature-based, technological. You just ramp this up, ramp this down, and it actually solves a bunch of differential equations in your browser. And then you immediately see how the climate system reacts. So this is super cool. I love the interactivity. It can be used greatly for teaching and so on. But again, we're in a situation where you can only change the things that the developer wants you to change, right? Because you don't have a hackable interface. You just have an interface where you have an existing button and you can change the button, and that's it. And so to summarize this, climate models are really used for, and this is in distinction to weather forecast models. Yes, there are some repeated workflows that we have, like running certain scenarios, like worst case scenario, how bad could it be with climate change? Sure, there's a lot of high performance computing benchmarks where you run the same stuff over and over again, as we also had a request basically earlier this morning. But there's also a lot of scientific one-off experiments, simulating counterfactual worlds, coming quickly up with an idea of like, you want to change this in this climate system, what would happen if a hurricane doesn't produce any rain, and you can basically see what it does to it. And all of these things are completely like counterfactual worlds, and so you really have to have interactivity to make that efficient. And just having a bigger computer doesn't necessarily help there. However, and I think it's always important to highlight the other side of it. So the advantage of a monolithic interface instead is really like having a simpler interface, right? You know exactly which buttons can be touched. It's definitely easier to design because you just say like, well, here are some buttons, use them. Providing a hackable interface that still like withstands all your crazy ideas is definitely a much harder one. And of course, then therefore, if you build I don't want to sit in a plane where you could be engineer and pilot at the same time. Of course, definitely not. But as long as we're not concerned that much about safety, I think that's, the monolithic interface is definitely not a way to go. And this is, I think, the important part, is that we are part of an open source community. Open source really lives from also just occasional contributors. And so we really want to tear down these walls between being a developer and being a user. If you create a monolithic interface, you're often creating a division between the two. And so definitely with climate modeling, with the interactive climate modeling, what we want to do is have a slippery slope so that every user can quickly become a developer. So we are kind of experimenting with these ideas with a package called Speedy Weather. Our tagline is play climate modeling like it's Lego. And so here's just like some videos that show you what Speedy Weather can do. There's here a global map of, maybe you can identify, I think there's, if my mouse can see here, this is, for example, then the Andes in South America, North America here. So this is some humidity. My favorite quote here is a colleague of mine, Pierluigi Vidale, wrote me at some point an email, like late at night, like unthinkable on such a small laptop, like playing a video game. And I think this is exactly what I want to get across. I want to have a model that is so fun that you can play it like a video game. So a simulation of cloud cover here, and in Speedy Weather you can also put particles in. So we heard the air quality simulations earlier. It's kind of the idea that you basically just put some particles in it, and you can just say like let the particles follow the wind, and then they just kind of fly around. That's exactly what it does. The kind of play climate modeling like it's Lego really comes from the idea that we do want to have, in the end, different building blocks and can put them together. Once you have these building blocks, you can also use just a Speedy Weather demo where we put everything into a Pluto notebook and then simply said like, well, let's choose some parameters. So you can basically, even though you have a hackable interface, you can then put a monolithic interface on top again, me creating some sliders. And the sliders are then, I mean, there's some hidden code here that says what the other ones are, like the two parameters that are here that are basically then directly used in the code below. And you can just basically then play around with them, and you see like I'm changing the resolution here and I'm changing the forcing parameter, and then a very idealized simulation here is just changing and immediately uses like Markey, and you can therefore kind of like very interactively optimize, oh, I want a bit more like this, I want a bit more like this, which is often, obviously, is not necessarily an objective way of optimizing a model, but it's often a very good start point to have an idea of what's happening. And having this in a quick way is obviously something that's super good. And so I believe with Speedy Weather, where are we in terms of speed on a laptop? I think we're pretty good. We have the GPU version up and running, but I put it in orange here because, like, in terms of performance, it's still a bit more work needed there. But it's definitely cross-platform. Like students install it in like 2 minutes on a Windows laptop. That doesn't cause any problems. I'll show you some examples now how it's like how it can also have easy extensions, how it's easy and interactive. I mean, the interactivity you can already see on the right. And some of the things how we want to tackle physical accuracy, especially through the integration of machine learning into this model. Speedy Weather is actually monorepo, where we took a good amount of inspirations from other monorepos that are also developed here in the room. So, for example, Markey. And so we have like a Speedy Weather internals. I guess many packages have like a core package or base package or so. And then we have several packages on top of it. They all sit in the same repository. So lower triangular arrays is basically an n-dimensional version of for like representing the spherical harmonics that we use to represent the spectral space of our model, as well as then ring grids is the package that we use for representing data on the sphere, which I guess is also relevant for a lot of people here in the room. And then transforming between the two, we have the Speedy Transforms package, and then Speedy Weather imports all of them. And so for ring grids, I thought I'd talk a little bit about it. So this is just an animation where I recorded myself playing. You see my mouse there, kind of like zooming around. This is just a HeelPix grid visualized with GLMarkey and GeoMarkey. And so ring grids basically provides you this interface. It's just something that you wrap around an abstract array. And it kind of just encodes for the first dimension where a grid cell is on the globe. But it's array agnostic, so you can put in, of course, a Julia array, but you can also put in any kind of GPU array. You can put other things in it. And then the kind of like the second to nth dimension are not further specified, so you can do basically whatever you want with them. And so we have things like the HeelPix grid implemented. We have also developed a new one, an octa HeelPix grid, which is a little simpler. So they're equal area, and I'll talk a little bit about them further. But especially we had to basically also build the whole thing with this being array agnostic, so that the whole thing becomes GPU ready. So that you can really just say like architecture equals GPU, and then you can use the same grids representing, for example, CUDA arrays. Maybe that's also something interesting for people here in the room. A lot of these grids are actually hierarchical. So that's something we worked on. So instead of just indexing the entire matrix by, for example, like an IJ or as a continuous index here with this ring order. Where's my cursor here? You see it goes like 1, 2, 3, 4, 5, and goes like a ring around the globe, which is super important for the transforms. But actually having a nested order can be sometimes really, really useful. So a 1, 2, 3, 4, so it feels like a space-filling curve. But it actually is in a way that it's hierarchical. So kind of changing the resolution becomes trivial because you just have to average 4 consecutive points in memory. or you just have to duplicate them 4 times, and then you go to like twice higher resolution or twice lower resolution, and therefore I hope that at some point the octa-heap script might be something which is really nice then, where we have basically equal, very efficient spectral transform, hierarchical, and everything is just one big square matrix in one go. Simona always complains about that these are not orthogonal grids, but like this is some details, but definitely we've been working on some of these things because we use them in order to represent our data inside Speedy Weather. At some point, and this is kind of looping back to what I said in the beginning, I would like Speedy Weather to basically have kind of like look like Windy, where you just say like I run the simulation, you can zoom around, you can look into, you could then like change the different fields. I want to look at sea ice now, I want to look at land and so on. That would be super cool. Or just say like I want to run the simulation for another 10 days and you see how it evolves then. So these things at some point to be added, maybe next year you'll see a play button in this one, that would be great. But otherwise this is just an existing geomarchy, GLmarchy, where I just have some field that was simulated by Speedy Weather, plotting the polygons. So this is also thanks to some work that Anshul did, just plotting the polygons, so there's actually no interpolation involved. It's just every field just has a color as a polygon, and they're basically all just put together with some coastlines on top for orientation. Exactly, the whole idea around modularity, flexibility, shown here again as a Pluto notebook, is super important. You see, I'm basically just literally say using Speedy Weather and GLmarchy, I'm creating the grid that just defines the resolution. I'm creating the model in the next line, and I can, in that model, I can say like convection, I can switch on and off convection, so different physical parameters. Surface humidity, I can switch that on and off or change the values of this. And I literally just initialize the model and run the simulation, and it happens in your notebook. And if we go back to the beginning, you see then basically how quickly everything updates, and it really lets you allow to play with it. But of course, and this is the important point for it, it is hackable. So you could, in every point in between those lines, you could always insert your own piece of code. And so you not have a predefined user interface. And so that was really important for us. I go through a couple of more examples. This is some work that one of my students, Greg Monday, pulled off in a day or two or so, where he just included surface roughness as learned through a neural network inside Speedy Weather. So surface roughness is basically, you need to know this in a climate model, because whatever your surface fluxes depend on how much turbulence there is, right? So if there's a lot of turbulence, like you can warm up the atmosphere quite quickly, or the flux goes the other way around. But the surface roughness is very different if you have a very calm ocean, if you have sea ice on top, or if you have rough ocean waves, or on land, whether you have like little grass or big trees. And so there's basically this surface roughness is usually something that we would load in from data, but we said like, well, we want to have a climate model. Why don't we just like try to learn this? And so it just has learned this. He literally just used just a PyTorch model, and then we just load this in as a first step. Of course, at some point we would love to do this more efficiently with Lux or so, but it clearly learned that there's, for example, no trees in the Sahara, that it actually needs to have a higher drag coefficient through the higher surface roughness where there's a lot of trees. So like in Central Africa, but also in like Siberia, or in like Canada up here in the Amazon and so on. And then other areas are lower surface roughness and therefore a lower boundary layer drag coefficient. That's what you see in the top. And then the bottom, what we just had before, where I literally just picked 2 values. I said like, well, on average, surface roughness is maybe like this over land and like this over the ocean. And obviously does a much better job. And this is something that we really, what we built Speedy Weather for. Is not like we want to throw the entire climate model away and just learn everything from data. No, we want to plug in a lot of small neural networks into different parts, so that always the inputs and the outputs have some kind of physical meaning. Therefore, we get rid of this whole idea of the internals of the learned climate model being a black box. And if we have a lot of small neural networks, we can basically really like design it in a way that respects a lot of the physics. And this is kind of what I believe is really cool here, and it would even support generalization. So you could move your continents around and you would still have it, and you don't need to load it newly from data and so on. This is one point I touched on earlier. I guess like the name speedy weather is almost like a bit, it's not inclusive enough now. Maybe we should call it speedy climate at some point. I guess that's not going to happen, but just to show you, we now have also a SLAP ocean model. So it's basically an ocean model where you just set all the velocity to 0, and the thermodynamic sea ice model, which I just showed here in the video. So it's a super simple sea ice model, but it basically does kind of okay job for given the simplicity. It's just like a few equations, but it nicely grows the sea ice in the respective winter hemisphere on either hemisphere, and also have a land bucket model so that it simulates like temperature, humidity, snow, so snow can be produced, falls down, and so on. And so the whole thing really becomes more as like an atmospheric model with simple representations of all the other spheres, and that was important for us. For the GPU stuff, and this is basically the last point I want to make before your coffee break, is that one thing I'm very proud of is like recent developments on the GPU stuff, where a lot of the parameterizations are written in a way that they can super easily be executed on the CPU as well as on the GPU without any code change. And so these few lines are basically how the albedo is calculated over the ocean using sea ice. In the end, it is a relatively easy formula, but we've written the whole code so that actually everything is quite self-contained. So you basically, if you want to implement a new thing, you literally just write top to bottom in one file some code, and you don't have to jump across different files and change different things here and there, which is obviously something that we realized is super important if you want to let your like model development scale. If you want to implement something new and you suddenly have to touch 500 different things, that's going to slow you down. That's going to like cause a lot of merge conflicts and so on and so forth. If you are able to write a new component that really just like reads basically top to bottom. So really this has like kind of like it has the doc strings in it. It has all the default values in it. It has one line that's important for the GPU code, like how to adapt this for so that the whole struct can be on the GPU. It has like the user interface as a constructor in it. It says like what to do when it's initialized, nothing. And also what actually needs to be done when it's computed, with a couple of, there's like a hash key that's actually compiled away and so on. And so this whole code can be executed on CPU or GPU. And you can, and I want to show this as a contrast to, maybe some of you have heard a couple of weeks ago, a month ago maybe, was the Gordon Bell Prize was given to a Fortran climate model. The Gordon Bell Prize for Climate Modeling 2025 went to Icon. And Icon is this like, okay, massively big model, everything has been developed, but there's one part in their paper that was then published in, what is it, one of the journals with this Gordon Bell Prize, and they basically talk about how they've written some of the kernels. And what absolutely struck me was like to see that actually A, it's completely unreadable. B, the lines of code that actually do things are fairly little compared to all of the lines of code that have to be added in order to get all sorts of like OpenACC, GPU statements in there. And so they really took this approach of like, there's an old school Fortran model, there's a loop, and I'm basically just like peppering around some kind of lines of code in order to tell the GPU compiler what to do with this line of code. And so what I think is a massive disadvantage of like what suddenly you basically have intertwined lines that are responsible for like the scientist writing the actual like algorithm, and then what they call performance engineer, and you kind of have to, but they kind of just turned this around and said like, we have a separation of concerns. And I think it's kind of not actually this, because you're conflicting two roles completely in the same code base. And so writing code where actually less than 50% are actually describing the calculation, I'm not sure that's the right thing to do. So I hope that we can write climate models that are better than that. Don't quote me on this. Thanks. Questions? Yes, that's one.
Now I'm being hated by everyone. Thank you very much for a wonderful presentation. My question is, you had question marks on the physical accuracy about the speedy weather. So my question is if in speedy weather, someone can actually play around with the equations, the differential equations that you're using, or is if this, you know, off the books and you're just not supposed to touch that? Thank you.
No, so you definitely can. But I'm hesitating a little bit because there are certain things that are a little bit more hard-coded than others. So with all the, like in an atmospheric model, a lot of emphasis goes to the parameterizations. So all of these unresolved physical processes, radiation, convection, precipitation, and so on. Those ones you can always like swap out, switch on and off, that's no problem. In the dynamical core, so that would actually solve your primitive equations that I've shown earlier, there is definitely a few of these terms you can just like switch off, you could change, but it's not as modular as, for example, like Oceananigans, for example, has the idea like you can run it in like a little square box, you can put your whole grid around the globe. Because of the numerical approach that we've taken, we're basically hard-coded to a sphere, so you have to always use a sphere. There are also obviously other, maybe you've ever played around with the Daedalus model in Python, which is super cool because you can basically just write, normal, like you can write your equations as like a string and it would translate that into code, and therefore you can basically execute any kind of operator, even though basically just like just chaining things together. We're not quite there in terms of the flexibility. So the idea is still that this is a model that should always solve a certain set of equations on the sphere. There is some flexibility of like tweaking those. You couldn't do everything, but you can still do a lot on the dynamical equations. But the emphasis is really on like the climate processes, so that they can always be super flexible, be switched in and out. Go ahead. Oh.
Yeah, I guess I'm kind of wondering, on a couple of levels. One, so this speedy weather is a simplified, heavily parameterized atmospheric model. To go from that to a full climate model is a gigantic task, one that the climate program sort of, ambition to do, and has had a lot of, time, manpower, funding, and developers involved in, and they are relatively far from their goal. Mm-hmm. So I guess I'm slightly uneasy about the notion that it's just about, switching to a different language that is going, and interactivity that's going to sort of get us there. I love the fact that all of this interactivity comes directly from Pluto and Mackie and Julia itself, and I'm totally on board with that. We've talked about this before in JuliaCon and others, but my question really is about, I'm always concerned with the ability for users to sort of break consistency within a model. Like a scenario whereby somebody takes speedy weather, mm-hmm. puts a few factor of 2 or 3 here and there because they decided this was smarter, call it speedy weather, write a paper, never contribute their code back, and kind of how do we, as a community, deal with this kind of, I guess, inopportune development?
Mm-hmm. So you're basically saying that if you were to write code that is so hard to use that you always need the main developer, then the information of a new development can't bypass the main developer. Whereas if you produce something that's like super easy to use, people can run away with it more easily. Is that?
No, that's not what I said. You could break a Fortran model just as well. Right? Yeah. I guess it's not the interactivity to me that leads to better science. It's the reproductivity more mm-hmm. so, and the checking on what the actual code does. Mm-hmm. And that is a difficult undertaking. Yeah. One that has nothing to do with the use of text files, interactivity, or even our ability to bridge between mm-hmm. users and developers. I'm sometimes worried about, I guess, scientific reproducibility is my question is about. How do you think about speedy weather in this context?
Yeah. I guess like a lot of what you basically mentioned, a lot of reproducibility comes from the fact that you can use it in many different ways, right? You can just like what basically Shenanigans engineered is like this idea that you don't have a name list anymore. You have like a script that basically just defines your whole thing top to bottom. So actually reproducing the exact same simulation is like, I mean, that's fine. Actually knowing what exactly executed, and if you, because it's such a complex system, and you just want to do an experiment kind of touching in one corner, making sure that this, what you're doing there is actually consistent with everything else, is I'm not sure whether there is a general easy way to kind of solve this. What I think at the moment, as like probably the best approach, if you make something really usable for someone, then they can go out and implement it. But then what I think is the best approach is to just kind of like, let's say, open an issue and let us know about it, what you did. And then we can kind of verify like, yes, that's kind of like how we would have done it too. Because of course, there's a lot of knowledge that you can't just all write down into documentation. It's very difficult to kind of like make something easy, but not leave out all the details. And I guess there is a discrepancy here. But at the moment, I think it is the best way is to like start easy, get your stuff implemented, and then kind of just ask for review from the people that wrote more about the code. But I'm not sure whether this is the best approach. It's a good question. Any last question? Coffee break. Coffee break. Good. Thanks.